we've proved the quotient remainder theorem, and so the next thing that I want to do is just look at some really quick and useful applications of this theorem. So here's our first one. It's about divisibility. So I have two integers, a and b, and what I'm going to say is that b divides a, right? And what that means is that a can be written as k times b for some integer k, right? So for example, 3 divides 24, okay? And the reason is because 24 is equal to 3 times 8, okay? Which is an integer, right? So that's what we mean by something divides something else, okay? Now the way we usually write that is to say b vertical bar a. So this is actually 3 divides 24. It can be written as 3 vertical bar 24, and that's what that's just a symbol for division, okay? And by the way, we say that a is equal to k times b. Because of the quotient remainder theorem, we know that the truth of k is unique, okay? And so is the 0, right? Because there is if it divides it, period. It's not possible that using one quotient we get a remainder 0. Using a different quotient we get a remainder 10. No, it's the quotient remainder theorem tells us that this is a reasonable definition, okay? So let's see what else we could do, okay? Suppose that a divides b and that also a divides c. Then we claim that a divides b plus c, okay? So for instance, 2 divides 10 and 2 divides 4, right? This should imply that 2 divides 14, which in fact is true, okay? So let's look at this proof. Because a divides b, b can be written as k1 times a, c can be written as k2 times a for some integers, k1 and k2. But then b plus c is just k1 plus k2 times a, right? And this is an integer. So since b plus c can be written as an integer times a, that means that a divides b plus c. End of proof. Okay, really straightforward. I like these. These are well, they feel good, right? Now there are some others that you should be able to prove just by following the same pattern. So if a divides b and a divides b times c, okay, then I'm sorry, if a divides b, then a must divide b times c for all integers c, right? So for instance, 2 divides 10, oops, 2 divides 10, well that means that 2 also divides 20, and 2 also divides 30, and so on, okay? If a divides b and b divides c, then a must divide c, right? So what we have is that 2 divides 10, and 10 divides 200. This means that 2 divides 200. Right? Okay. And finally, if a divides b and a divides c, then a divides m times b plus n times c, where m and b are any integers. Okay. You can actually prove this from this theorem that we have here, and then from the one that you can just multiply something by any constant, or you could prove it from scratch. Okay. But all of these are nice little theorems about divisibility. Okay. Here's another kind of important property that has more of the feel of a definition. Okay, so a and b are integers. A can be written as q times b plus r for some integers q and r, such that 0 is less than or equal to r less than b. This actually is, right, the quotient remainder theorem, right? You know, so suppose that this is true. Well, let me know that's true. Okay, so now here's the new part. R is the remainder of a modulo b, and we write r is equal to a mod b. Okay. Now here's a couple of things I want you to know. Mod is actually a function. Okay. This is kind of similar to saying r is equal to a minus b, for example. Okay. That is mod. Okay. It's a function. It's an operator. Okay. So it would have been better to write it as mod of a comma b, right? Or even as a percent b, where percent is an operator like minus or plus, right? But the old notation is just going to stay with us. It's kind of a famous notation for modular arithmetic, so that's the way it will stay. Okay, and I did say that it was a function. Why do I know that it's a function? Well, I know it's a function because the values are unique, right? You know, so if you give me a and b, then a mod b is a unique value, and that's because of the quotient remainder theorem, right? So that's why that again, that theorem is at the heart of this particular statement. Okay, so here's another theorem that I think is very useful. Take a1 and a2, and these are integers, and b is a positive integer, okay? And so what I want to show is that A1 mod B is equal to A2 mod B if and only if A1 minus A2 is a multiple of B, right? Okay, so let's do it, part one. Okay, so so this is kind of the if part. So we're going to assume this, A1 mod B is equal to A2 mod B, right? So what does that mean? Well, that means that A1 is written as K1B plus R, and A2 is written as K2B plus R. Okay, why is that? This is the remainder, right? And what we know is that the remainder of A1 and R, right, is actually equal to the remainder of A2 and R. Okay, that's what we're assuming. So yeah, I can just call it R in both cases. Okay, but then once I do that, what happens is that A1 minus A2 is K1 minus K2 times B, just rearranging terms. Okay, and what do I get? Right? Well, that means that A1 minus A2 is actually equal to K times B, which is what I was trying to show, right? For some K, right? It doesn't actually matter what the K is, but yeah, it's some integer, right? So great. So we got that part. Now let's try to do the other part. Right? Go the other way. So let's suppose that A1 minus A2 is actually equal to KB for some integer K, right? All right, so I can rewrite that. A1 minus KB is equal to A2. Okay, that's just that's just the same condition, right? A1 minus A, right? All right, so A1 is equal to K1B plus R1. Okay, A1 is equal to K1B plus R. Rather, A2 is K1B plus R1. This is just A1. Okay, minus KB. Right? And that means, after I combine the b's, that this is like KB plus R, right? Okay, and that's where the quotient remainder theorem comes in. I managed to write A2, right, as KB times R for some K and B. The actual values are not important. I mean K and R. Okay. What is important is that because I was able to write that, and I have that 0 is less than R1, less or equal to R1 is less than B, right? That's part of what I got. Then guess what? That's unique. That's the only way to write it. Okay. So what that means is that R1 has to be equal to A1 mod B. There's no other choice, right? Because of the uniqueness of the quotient remainder theorem. That means that A1 mod B is the same as A2 mod B. So that's actually what R was. It was the remainder when I divided it by B. So the quotient remainder theorem again lets us say this really nice property that if I have two integers and their remainders are the same when divided by B, then in fact the difference between those is a multiple of B, right? And vice versa.